The next application is that of taking a large collection of fingerprints and finding which pairs are from the same person. Usually, fingerprint analysis is not a many-to-many problem where we have to find all matches at the same time. Rather, we organize a database of known fingerprints, and when a new fingerprint comes in, we try to match it to those we have seen before. However, the LSH technique is still an excellent way to organize the database so that we have to look for matches to the new fingerprint in only a few buckets. To start, we should know a little about how fingerprints are represented. An image of a fingerprint is examined for what are called minutiae. These are particular locations where something interesting happens to the ridges that form a fingerprint. Examples are where two ridges merge into one or where a ridge ends. So the image of a fingerprint is replaced by a set of coordinates in a two-dimensional space where minutiae are located. You place a grid over each fingerprint image. The grid must be scaled and oriented properly so that if you have two images of the same fingerprint, perhaps one at a different angle or a different size, the grids will overlap. Then you represent each fingerprint by the set of grid squares that contain minutiae. Since some minutiae will be right on or near a boundary, it is useful to regard such minutiae as present in the squares on both sides of the boundary. So it looks like we have reduced the problem of finding matching fingerprints to the problem of finding similar sets of grid squares that have minutiae. The problem is that the resulting matrix is not sparse. The grid cannot be too fine or it will be unclear where minutiae belong, and as a result, the matrix whose rows are the grid squares and whose columns are the fingerprint sets will not be sparse. That means min-hashing will not work very well. Each min-hash will have relatively few different values, so we don't get a good distribution into a large number of buckets when we do the LSH. We're going to have to twist things a little bit to get LSH to work. So before proceeding to the solution, here's a picture of what minutiae look like. This is a case where two ridges merge into one, and the entire fingerprint has been overlaid with a grid. It appears the point of merger lies within this grid square, so we add that square to the set representing the fingerprint. However, we might also want to add the squares that are very close to the exact point of merger, because in another image of the same fingerprint, the grid might be shifted slightly to the left or down. Remember that we represent fingerprints by sets of grid squares, those with minutiae. We could min-hash these sets, but there is no need to. The universal set is the set of grid squares, and the grid is not too fine, so there might be hundreds or at most thousands of squares in the grid. We can thus represent each set by a bit vector with one position for each square. The ones represent squares with minutiae, and if there are, say, 1,000 grid squares, then each bit vector takes 125 bytes. That's much less space than, say, a vector of 100 integer min-hash values. For our LSH, we pick some number of sets of grid squares or components of the bit vectors that represent fingerprints. In our example, we'll use 1,024 sets of 3 grid squares each, which seems to be a good choice. For each set of 3 squares, we look at all the prints that have minutiae in each of these 3 squares. In a sense, we are throwing fingerprints into buckets, but each set of 3 squares corresponds to one bucket. And unlike a hash function, a fingerprint can be placed in many buckets. In fact, it would be normal for a print to be placed in several buckets this way. To see why the numbers we proposed make sense, let's look at a typical situation. We'll suppose that approximately 20% of the squares hold minutiae. Also suppose that if 2 fingerprints represent the same finger, then at least 80% of the squares with minutiae from one also have minutiae from the other. The fact that we place minutiae in nearby squares if they are at the boundary helps make this assumption true. Let's see what it takes for the bucket corresponding to a set of 3 squares to receive 2 different fingerprints. First, if the fingerprints come from different fingers, then the probability that both prints are placed in this bucket is really tiny. For each fingerprint has a 20% chance of having minutiae in each of the squares, so the chance of it hitting all 3 is 0.2 cubed. And for both fingerprints to hit, the probability is the square of that, that is 0.2 to the 6th power, or 0.000064. Now let's look at two fingerprints that come from the same finger. The probability of both being in a given bucket is much higher. The reason is that there's a lot of correlation between the buckets that will contain these prints. To start, for any given grid square, the probability that the first print has a minutia there is 0.2. And given that it does, the probability that the other does as well is 0.8. We need to raise 0.2 times 0.8 to the 3rd power because there are 3 squares, each of which need to hold minutiae from both of the prints. The result is about 0.4%, still really tiny, but 64 times larger than the probability if the prints come from different fingers. But remember, we have 1,024 sets of 3 squares each. In order for a pair of prints to be a candidate pair, we have only to find them together in one of these 1,024 buckets. The probability of that happening at least once is 98.5%. You can do the math if you like, but there's an outline on the slide. That means there are only 1.5% false negatives. On the other hand, the same calculation for a pair of fingerprints that comes from different fingers is this, and it gives them a much smaller value, 0.063. That is, there will be only 6.3% false positives. That's still quite expensive. It means that 6.3% of all pairs need to be checked for similarity, when almost all of them will not be similar. On the other hand, we did reduce our work by a factor of 15, and by using a larger number of sets of squares, or perhaps 4 or 5 squares per set, we can reduce the false positive rate substantially while still keeping the false negative rate low.